In this video, we're going to start looking at the molecular geometry or the shape of my molecule. So the shape of molecules. Right, my molecular geometry. I'll use both of these terms. So do know that if I say geometry, I am talking about the shape. Right? What does it look like in three-dimensional space? So how are the electron groups oriented in three-dimensional space? Remember Lewis structures or electron dot structures. This tells us nothing about the shape. We need to be able to draw Lewis structures to be able to determine the shape, but the Lewis structure itself doesn't tell us the shape. Remember, the Lewis structure just tells us how the valence electrons are distributed in that molecule. Essentially, it tells us what atoms are connected to what atoms, or which atoms are connected to which atoms, how the atoms are connected. Are there single bonds, double bonds, triple bonds, lone electron pairs, also called non-bonding pairs, etc., right? It tells us nothing about the shape, just how are they connected, right? In water, is oxygen in the middle, is hydrogen in the middle? Hydrogen can never go in the middle. How are they connected? What types of bonds are between them, right? Single bonds, double bonds, triple bonds, lone pairs. But it tells us nothing about the shape of the molecule. To determine the shape, what we're going to do is we're going to use Vesper Theory. And I do have a handout posted on Canvas for you. So just like we did with the Lewis dot structures, if you wanted to pause the video, if you have a printer, go print it and then come back. If you don't have a printer, that's fine. You can just copy it down. Again, you'll probably have to hit pause a few times to get everything copied down. I'm going to be going back and forth between this handout and the other page where we'll work through some examples. So Vesper, it is an acronym, so the VSEPR should all be capitalized. And it stands for Valence Shell Electron Pair Repulsion. And I'm not going to test you on what it stands for. I just find it easier to understand how the theory works if I remember what it stands for. So remember, we don't have dots and lines and little H's and little O's, right? It's groups of charge, right? Each bond is negative charge. Each lone pair is negative charge. And one bond, right, its negative charge is going to repel a neighboring bond because like charges repel. So our shape is going to be based on the fact that electron groups, right, double bonds, triple bonds, single bonds, lone pairs, are going to repel each other. So if I have two groups of electrons, they're going to try to get as far apart from each other in three-dimensional space as they can, and they're going to be 180 degrees apart, right, because that's as far as they can get. If I have three groups of charge, they're going to try to get as far apart from each other as they can, and they're going to have 120 degree bond angles. So my shape is just based on the fact that electron groups repel each other. They want to get as far apart from each other as they possibly can, and that's what my shape is going to be based on. So to determine the shape, first of all, we have to be able to draw the Lewis structure, because if we can't, I don't know how many electron groups I have, right? I need to know how many bonds I have. I need to know how many lone electron pairs I have. Once we draw the Lewis structure, we're then going to determine the number of electron groups, also called charge clouds. And then they're also called electron domains. I don't use this term very much, but I know in lab they do. So an electron domain, an electron group, and a charge cloud are all the same thing. So we're going to draw the Lewis structure. We're going to determine the number of electron groups or electron domains on the central atom. We're going to look at the one in the middle. If there's more than one central atom, then each of those central atoms will have a shape, so we'll look at all of them. And then what comprises an electron group? A lone pair, a single bond, a double bond, and a triple bond are all one group each. So even though a triple bond contains 6 electrons, it's in one location, so it's going to count as one group. So an example, if I was to draw out my Lewis dot structure for this molecule, so HCN, and I'm going to look at my central atom, which is carbon, and carbon is going to have 2 electron groups. I have a single bond and I have a triple bond, so that's 2 groups. So my shape for this molecule is going to be based on 2 things repelling each other. It's actually going to be 180 degrees. It's going to be a linear molecule. If I was to look at, let's say, H2S, if I was to draw the Lewis dot structure for this one, after you go through the rules, we end up with this structure. And my central atom is sulfur. It has 1, 2, 3, 4 electron groups on it. So draw the Lewis structure, determine the number of electron groups. A single bond, a double bond, a triple bond, and a lone pair are one group each. Once you do that, you determine the shape based on those groups repelling each other. So this table is what we're going to use. I do want you to be able to determine the shape without using this table, so I do want you to learn these. Once you go on to other chemistry classes, you're not going to be able to use this. They're going to expect you, if I give you CH4, I expect you to know that it's tetrahedral without pulling out a chart. So you do need to become familiar with this. So we're going to go through some examples. I do have examples on the next page here. I'm going to work through these. So they're already answered here for you, but I want us to work through them together. So we'll be going back and forth between those two. So my first one is carbon dioxide. And for all of these, I'm just going to give you the Lewis structure. But if you need practice, which I assume most of you are, what I would do as soon as I write down CO2, hit pause, draw the Lewis structure yourself, and then compare it to what I get. Because if you can't draw the Lewis structure correctly, you're not going to get the right number of electron groups. And if you don't get the correct number of electron groups, you're not going to get the correct shape. So I'm going to draw the Lewis structure, but please try it on your own first. Then hit play, and then come back and look. So for carbon dioxide, when I draw my Lewis structure, I end up with carbon in the middle. I end up with a double bond to each carbon, and then 2 lone pairs. So when you're drawing these, please go through those rules I gave us, right? Determine the total number of valence electrons, figure out how they're connected, connect them with single bonds, put lone pairs on the outside atoms, right? The terminal atoms, so each has an octet. If you have extra electrons, they go on the central atom. And then our last step, if atoms that want an octet still don't have an octet, you're going to rearrange your electrons to add double or triple bonds. And when we do that for carbon dioxide, I get this as an answer. If you got this, it is also correct. It's not the best structure. This other one's better for reasons that you'll learn in organic, honestly, but it is also a correct structure. We're going to get the same shape whether I use the one with the 2 double bonds or the one with the triple bond and the single bond. Okay, so to figure my shape, what I'm going to do is I'm going to look at that central atom, and my central atom has 2 electron groups, right? I have 2 double bonds. I have a group here and a group here. Those 2 groups are going to repel each other. They're going to try to get as far apart from each other as they possibly can. And I actually drew the shape here when I drew the Lewis structure. They're going to have 180 degree bond angles. And then the name of that shape is going to be linear, right? It's just in a straight line. So linear. So I'm going to go back to that table real quick just to kind of see how it's working. I have 2 electron groups total. Both of those were bonds. I had no lone pairs in my central atom. They want to get as far apart from each other, so 180-degree bond angles. Name of my shape then is linear, and then the carbon dioxide example. The next one we're going to do, I'm going to draw BH3, and I'm going to do the Lewis structure. Again, please try that on your own. So my Lewis structure, I end up with this. Boron was one of the ones that was okay with not an octet, right? Boron was okay with just 6 electrons. So this is a correct Lewis structure. When I count my number of electron groups, I have 3 of them, right? We're looking at that atom in the middle, which is boron, and I have 1, 2, 3 groups. We are going to start differentiating between bonds and lone pairs. So I have 3 electron groups. All of them are bonds, no lone pairs. So I have 3 things repelling each other in 3-dimensional space. When that happens, I want to have 120-degree bond angles between them. So you don't have to get out a protractor and measure them, but make sure they are close, that they look like they're 120, right? This is closer, what I just drew in blue is 120. What I have over here in purple, those are 90-degree bond angles. If you draw it like that and tell me that that's its molecular geometry, I'm not going to give you credit for it because that is not its molecular geometry, right? I have 3 groups trying to get as far apart from each other as they can, and this group and this group can move up a little bit and get further away. So kind of going back, this is my Lewis structure. And when you drew this, if you would have put boron in the middle and, you know, done this, it's equally correct, right? Remember, as long as boron's in the middle and I have my 3 bonds to hydrogen, we're good, right? It has nothing to do with the shape. So my Lewis structure, this is my molecular geometry. So just be really careful. If it has 120-degree bond angles and I ask you to draw the geometry, I want you to make your best attempt at 120-degree bond angles. And if you draw this and tell me that's the best you can do, I'm not going to believe you because you can do better than that. So let's put our bond angles on there. 120 degrees. And all of these are 120. You don't have to label all of them, but all of those are 120 degrees. The next one I'm going to do is ozone, so O3. Again, hit pause, draw the Lewis structure, and then come back and check. So this one we go through and draw our Lewis structure. You should have ended up with a double bond on one side and a triple bond on the other. It doesn't matter which side you have it on. So if I had, not triple, a single bond on one side, a double on the other. So if you had the double right here and then the single right here, that's fine. But one oxygen should be in the middle, a single bond to one oxygen, a double bond to another oxygen, and then there is a lone pair of electrons on the middle oxygen. This actually has some charge to it, but we'll go and add that later. So the number of electron groups on my central atom, so I'm looking at the oxygen in the middle, I have a single bond, I have a double bond, and I have a lone pair. So that is 3 electron groups. 2 of those are bonds, and then 1 of those is a lone pair. So it's still 3 groups repelling each other, right? It's still based on this basic shape. So that's pretty ugly. I have an atom in the middle, right? And then I have 3 things repelling each other. So my electron domain geometry, we could say, for all of my 3 electron groups are going to have this basic shape. And you have to have atoms there. I'm just leaving it generic. Like it could be a boron in the middle and 3 hydrogen on the outside. I could do a carbon in the middle, a double bond to an oxygen, a single bond to 2 other oxygens, whatever it happens to be. But there's going to be an atom in the middle, and then there's going to be atoms or lone pairs in those 3 spots. So what we're doing with ozone is essentially I'm going to take an oxygen and I'm going to put one in the middle, okay, because there's an oxygen in the middle. I'm going to have a single bond to another oxygen and then a double bond to the other. And then where this is, I'm going to have my lone pair. And I could have put the 2 oxygens here if I wanted, and I could put the lone pair, in this spot if I want. It doesn't matter as long as 2 of those spots are my bonds to oxygen, and then one of those spots is my lone pair. But all of my 3 electron groups are going to have that basic structure. So I'm going to put the lone pair on top just because I'm kind of a creature of habit and that's where I always do it. But by all means, put it someplace else if you want. So I'm going to have oxygen in the middle. I'm going to go down to an oxygen. I'm going to go down to my other oxygen. Now remember that those are really close to 120 degree bond angles, so do not do them linear, do not draw them 90 degrees. Do your very, very best to make them 120 degrees when I ask you to draw them. And then for lone pairs, I do want us to put an electron cloud around it. Remember, our electrons are in orbitals, so I do want us to put an orbital around it. Don't just do the dots. The dots are fine when you're doing Lewis dot structures, but when we're drawing our shape, right, our molecular geometry, I do want to see those little clouds around my lone pair. So put them in an orbital. There are lone pairs here still. So this would be my molecular geometry. And my bond angle is actually going to be a little bit less than 120 degrees. What happens is because these 2 electrons, right, my lone pair, are not being pulled to 2 different nuclei, right? These electrons are being pulled to this nucleus and this nucleus. But my lone pairs are just sitting there. So they actually take up a little bit more space. They kind of puff out, which is the other reason I want us to draw that electron cloud. Because those lone pairs take up a little bit more space, it's actually pushing those bonds a little bit closer to each other. So that angle between my bonds turns out to be a little less than 120 degrees. So less than 120. I'm just gonna get rid of the green here and make it look normal again. So electron cloud with my lone pair. Do be careful, bond angles are the angles between bonds. They're not the angle between a bond and a lone pair, right? They're called bond angles, not lone pair angles. So be careful. If you were to label your bond angle here, I'm actually going to mark that incorrect because it is incorrect. So for BH3, all of 3 spots was a bond angle because there was bonds in all 3 spots. With ozone, O3, I only actually have 1 bond angle, right? If I was to label it over here, I'm not labeling a bond angle because this is not a bond. So again, be careful. If I ask you to label bond angles, make sure you label bond angles and not things that are not bond angles. So I never gave you the names of these. Let me add that to it. It is on the table, but let's put them here too. So the BH3, its name is trigonal and then planar. And you do need both parts. You can't just say trigonal because we're going to have things that are trigonal that are not planar. And you can't just say planar because we're going to have things that are planar that are not trigonal. So I do need both of those. So trigonal planar is the name of that shape. Trigonal because I have 3, right? We can go over to this one. I have 3. 1, 2, 3. And then planar because it's flat. Nothing's sticking up at us. Nothing's going back. It's just completely planar. It's only 2 dimensions. You could draw it in the plane coming in and out of your paper or the screen, but then nothing would be going up or down, right? So just planar, 2 dimensions. So 3 things in a plane, so trigonal planar. The name of this one is bent. And that one's easier to remember if we go up here and look at this one that's linear. Linear means I have essentially 3 atoms in a straight line. This one, I have 3 atoms, but it's not in a straight line, it's bent. Also called angular. You may have learned it that way. I don't use that one very much, but bent and angular are the same. So either one of those are correct. And that's it for our 3 electron groups. So going back out to that table, what I would do is I'm going to draw that basic structure in this little box. It helps me to remember them. We're going to do that for all of these if I have kind of that basic shape. So if they're all bonds, I'm going to essentially have an atom in all of those spots. If 2 are bonds and 1's lone pairs, then I'm going to have an atom in 2 of those spots and then a lone pair in the other spot. But they're all going to have that basic trigonal planar structure. So kind of the way that you'll do it in labs, you'll actually say that your electron domain geometry is going to be trigonal planar. And then if you're talking about the shape of the molecule, that's where we're going to differentiate between lone pairs and bonds. But everything in this box for 3 has this trigonal planar shape. We can add a column maybe that says that. So trigonal planar. This one, linear. And again, I don't use electron domain geometry, but they will use this in lab. I guess we should make that heading in black so it's not so confusing. Okay, so 4 electron groups are on to our next box here, and I'm going to go back and we'll work out our examples. So CH4, and then again we need to draw the Lewis structure, and when I do that I end up with carbon in the middle and bonds to 4 hydrogens. So this one is going to have 4 electron groups, right? I have 1, 2, 3, 4. All of them are bonds, so 4 bonds, 0 lone pair. And for this one, this is going to be the first one where we need to remember that the world is not planar, right? It is not flat. Everything we've drawn so far has been planar, right? Nothing coming up at us, nothing going back behind, but we do have that space available to us. So for this one, what we're going to end up doing, and this is going to be for all of the ones that have 4 electron groups, so I'm going to kind of draw the little generic version. Let's do this one first. I'm going to have 2 in the plane. So I have 1 going straight up, and it doesn't have to be straight up. I just find, again, if I do it the same or similar every time, I'm going to make less mistakes. My bond angles are actually going to be 109.5, so don't do 90. If you do that, it's 90. Don't do this because it's 180, so do it something in between there. And then I'm going to draw a wedge, and this wedge means it's coming out at you. And I do have a model that I'll show us here in a few minutes. After I go through all the 4 electron groups, we'll get the model out. And then I'm going to draw a dash, and that means it's going back. So I have 2 bonds in the plane. I have 1 bond coming out at us and 1 bond going back. And you don't have to draw it. You know, if I wanted to do this one in the plane, and this is my other one in the plane, then I could draw this as my wedge and this as my dash. That got kind of ugly. You know, I can draw it upside down from how I have it if I want to do the mirror image. Right? All of those are fine. You just need to make sure that you have 2 in the plane with roughly 109.5 degree bond angles. And then the one coming out and the one going back are also 109.5 degree bond angles. I tend to either draw this version or this version. When I start drawing them upside down, I don't do a very good job of drawing them. I just don't have as much practice. So my bond angles I just said were 109.5. And all of them are. I don't have any lone pairs, so I can label this any place I want. If I want to label it here, or here, or here, or from this one around the back to this one. All of those are going to be 109.5 degree bond angles. And then my name is going to be tetrahedral. That's a D-R-A-L if you can't read my handwriting, so tetrahedral. It is spelled out on that handout. So our kind of little generic one, 2 in the plane. I'm going to have 1 coming out at us and then 1 going back. That's pretty messy. Let's see if we can make that a little bit nicer. So 2 in the plane. Again, feel free to draw it upside down from how I'm drawing it, or sideways. Just make sure that your bond angles are not 180 and not 90. And then you do have to have a wedged one and you do have to have a dashed one. My next example, on your handout, I do have NH3. I'm going to do NF3 just because I've been doing a lot of hydrogen. I want you to practice doing the loose dot structure with something else besides hydrogen. So again, try drawing the structure on your own. And then, went back to hydrogen. You should have gotten nitrogen in the middle. All of those fluorines have a lone pair on them. And then I have a lone pair on nitrogen. So 4 electron groups, right? 1, 2, 3, 4. Again, we're just looking at the central atom. So 4 electron groups. This time, 3 of them are bonds, right? The bonds to the 3 fluorines, and then 1 is a lone pair or non-bonding pair. So again, it's going to be everything with kind of in an electron group category. So these both have 4 electron groups are going to have this basic shape, right? This would be my electron domain. Electron domain geometry is tetrahedral. So kind of the same thing we did with the 3 electron groups. I'm going to have nitrogen in the middle for this one. 3 of those bonds are going to go to fluorine, and then 1 of those positions is going to be my lone pair. I'm going to put the lone pair in the top position, but honestly, you can put the lone pair in any of those positions. If I want to have a lone pair coming out at you, out at us, that's fine. You're just going to have to wedge that electron cloud, and I can show you how to do that. So I'm going to have nitrogen in the middle. I'm going to have a fluorine. It's got to be sloped down. I have a fluorine coming out at us, and then I have a fluorine going back. And then I do want to see that orbital around that lone pair. And then all my lone pairs on my terminal atoms. And that's what I'm going to get for my geometry. My bond angles. Again, that lone pair is going to take up a little bit more space. So it's going to push those bonds closer to each other, so less than 109.5. And then for this one, be careful when you're labeling a bond angle that you actually label a bond angle and not a lone pair angle, right? So I could label it here, or I could label it from here back around to the other side. I cannot label between a fluorine and the lone pair. I mean, I guess I could, but I would get it marked wrong. If you want to be correct, you cannot do it that way. And then the name of this one. I have 3 things, so trigonal again, right? By things, I mean atoms that it's bonded to. Sorry, I'm bonded to 3 atoms, so trigonal. And then it's not planar this time. It's not flat. It looks like a little pyramid. And I promise we will look at models so you can kind of see how that works, but trigonal pyramidal. So basically, this is like a little pyramid, if I could draw, which I can't do, but it looks like a little pyramid. It's supposed to anyway. I just want to get rid of all that purple I just made my pretty structure ugly with. And then one more in this category. And then I promise we'll look at models. So water, H2O. We drew this Lewis structure in a previous video. So I have oxygen in the middle, bonds to 2 hydrogen and 2 lone pairs. So I still have 4 electron groups. This time 2 of them are bonds, and then 2 of them are lone pairs. So again, I'm going back up to this basic structure. I'm gonna have oxygen in the middle, I'm gonna have hydrogens in 2 of those spots, and I'm gonna have lone pairs in 2 of those spots. It doesn't matter which are which. So I'm gonna draw this one 2 ways. I'm gonna do oxygen first in the middle. Well, oxygen's always in the middle, but I'm gonna do oxygen in the middle, and then I'm gonna do my hydrogens in the plane first, because I said I would show you how to wedge lone pairs. So what that means is one of my lone pairs is gonna come out. So what I'm gonna do is I'm gonna kind of shade the end of my orbital. And then I have a lone pair that's going back. So I'm going to dot my orbital. So I can draw it like that if I want. Or I could have the lone pairs in those 2 positions. And then I'm gonna have a hydrogen coming out at us. And then a hydrogen going back. My bond angles, bond angle, only 1 this time, right? Still less than 109.5 degrees. Every time you add that lone pair, your bond angle is going to be less than whatever it was when you didn't have that lone pair. I kind of ran out of room to fit this in here, so I'm trying to rewrite it. Okay. The name of it, I have 3 atoms in a row again, but it's not linear, it's bent. No matter which one you look at, it's bent. So the name for this one is also bent or angular. So going back to our handout here, I'm going to draw my little skeleton here. So 2 in the plane, 1 coming out, and then 1 going back. And the name of that, tetrahedral. And then again, every time you add a lone pair, just replace one of those bonds with the lone pair. So let's look at some models for this one. Hey, so I have a tetrahedral molecule for us, and I just kind of want to show kind of the tau tour in the plane. So I'm just going to use my periodic table as the plane. So the white one and the purple one, I'm going to have flat. So I'm resting them against the periodic table. And then if I turn it, we can see that the green one, my hand's on it, but it's going back behind that plane. And then the orange one is coming forward. So 2 that are completely flat, they're resting against my table, and then 1 coming up and 1 going back. And then of course, how I said you can draw it upside down or sideways, right? If I wanted to turn it upside down, my hand's totally in the way now. I have 2 in the plane, right? 1 coming out and 1 going back. But all of these bond angles, it doesn't matter which one, right? Between the green and the white, between the white and the orange, between the orange and the purple, between the purple around the back to the white, they're all 109.5 degree bond angles. And then every time we replace a bond with a lone pair, we're literally just doing that. So in my NF3 example, I'm taking up this bond and I would have a lone pair here. So there is something there, right? I don't have any electron clouds, but I would have an electron cloud there. And then it's considered trigonal pyramidal, right? I have 3 things, and let's see if we can make it flat here. If we look, right, there's space between the central atom and the periodic table. So it looks like a little pyramid. Trigonal planar ones, this central atom would actually be resting right on the periodic table. It would be planar. But this isn't planar, right? It goes up to make a little pyramid. And then when I make water, I'm just taking another one off. So I'm literally just replacing another bond with a lone pair, and now it's bent, right? We could draw it bent like that. I could draw it bent like this. It doesn't matter, but I have three things, and instead of being linear, they're bent or angular. So again, going back to my tetrahedral structure, every time I have 4 electron groups, this is going to be the orientation of those 4 groups. And then if one of those groups is replaced with a lone pair, I have a lone pair in that spot. If 2 of the groups are replaced with a lone pair, then I have lone pairs in 2 of those spots. 5 electron groups next. So let's go back to the other sheet. And we're going to use PCl5 as our example. And again, please practice drawing the Lewis structures for these. What I got is phosphorus in the middle, and then I have a bond to 5 chlorines, and then all of those chlorines will have 3 lone pairs on them. I don't have any lone pairs on phosphorus. So this is going to have 5 electron groups, right? I have 5 single bonds to phosphorus. And then all 5 of those spots are going to be bonds. And I have no lone electron pairs or non-bonding pairs. So when we draw this one, I'm going to have phosphorus in the center, right? I have 5 groups repelling each other. And then I'm going to actually have 2 different types of bond angles. So I'm going to go up to a chlorine and then down to a chlorine. And then I'm going to, on one of the sides, go out to a chlorine. So I do have 90-degree bond angles here. And then around the middle, I'm going to have another one coming out. And then I'm going to have one going back. So essentially what I have is between the top chlorine and all of the chlorines on the side, I have 90-degree bond angles. And then between the bottom chlorine and all of the chlorines on the side, the ones kind of around the middle, those are also 90-degree bond angles. So between here and here is 90. And then between here and here is also 90. I'm going to draw these and then erase them. Between here and here is also 90. Between here and here is 90. Between here and here is 90. And then between this one to this one is also 90. We will look at a model for this. And then all the ones around the middle, those are 120-degree bond angles. So that's 120. This one here is 120. And then this one around the back to that one, 120-degree bond angles. So I have 90-degree bond angles and 120-degree bond angles. The name of this one, Trigonal, I have 3 in the middle, right? It's like a little triangle right there. So Trigonal. And then it goes up to a pyramid. And then it also goes down to a pyramid. So the name of this one is going to be Trigonal Bi Pyramidal. Bi because there's 2 pyramids, right? I have a triangle for a base, and then up to a pyramid and down to a pyramid. So Trigonal Bi Pyramidal is going to be the name of the shape. And then again, 2 different bond angles. I do have different names. I'm going to draw our kind of generic version that we're going to use for all of our 5 electron groups. And then I'm going to actually put names on these. So I'm going to have one coming out at us and then one going back. The ones that go straight up and straight down are actually called axial positions. So AX, let's actually move it over here. AX is axial. And then the ones around the middle are called equatorial positions. So I'm going to put an EQ. So the bond angles between the axial and the equatorial positions are 90 degrees. The bond angles between an equatorial position and another equatorial position is 120 degrees. It's probably the easier way to say that. But again, our kind of version that we're going to be using as we replace bonds with lone pairs, right? It's essentially that. So our little triangle in the middle, up to a pyramid, down to a pyramid. And I do want to pause here and look at this one right now. So here we have our Trigonal Bi Pyramidal structure. So if I tip it sideways, right, I have 3 around the middle. So 1, and then 2, and then 3. And they do have 120-degree bond angles. And those were my equatorial positions, right? This is the orientation I normally have it in, but I'm just tilting it so you can see that there are 3. So 1, 2, 3, 120-degree bond angles between here and here, here and here, and here and here. So if I tip it back up, right, between this position and this one around the back, and then this one here around to this one. So those were my equatorial positions. And then my axial positions were the top and the bottom, and I do have 90-degree bond angles between those and my equatorial. So between here and here is 90, between this one and this one is 90, this one and this one is also 90 degrees. And then if I hold on to my top axial position, between equatorial and the axial on the bottom. So 90 degrees between there and there, between here and here, and then between here and here. The way that I've been orienting it, right, I'm going to draw 3 in the plane, so I'm going to use my periodic table as the plane again. So this one equatorial and then my 2 axials. Let me get my hand out of the way here. So those are flat up against my periodic table, and then if I turn it, the one that my hand is on is going back behind that plane, and then I do have this one here coming out in front of the plane. So my Trigonal Bi Pyramidal structure, right? Trigonal, 3 around to the middle, comes up to a pyramid and then down to a pyramid. Continuing with our 5 electron group examples. So Sulfur Tetrafluoride is going to be our next example. And again, please practice drawing these Lewis dot structures. If you don't draw these correctly, you're not going to get the correct number of electron groups. So I ended up with my sulfur in the middle, right? It's the less electronegative of those atoms. I have bonds to my 4 fluorines. I have 3 lone pairs on each of them, so each has an octet. And then we do end up with 1 lone pair left over. There's 2 electrons left, and our rule said to put that on our central atom. So I have 5 electron groups, right? 1, 2, 3, 4, and then 5. Of those 5 electron groups, 4 of them are bonds, and then 1 of them is a lone electron or non-bonding pair. So we're going to do a very similar to thing what we've been doing, right? We're going to take our structure, right? And we're going to replace one of those bonds with a lone pair. And when we did it with our trigonal planar and our tetrahedral domain geometries, I said it didn't matter. With this one it does, because I do have 2 different types of bond angles, right? Between my axial and my equatorial, it's 90 degrees. And then between my equatorial and other equatorial positions, it's 120 degrees. Remember that lone pairs take up more space than my bonding electrons do, so I want to put them in the position that gives them the most space. So for this one, I want to put them in my equatorial positions. So with our 5 electron groups, every time you replace a bond with a lone pair, it must go in an equatorial position. So lone pairs must go in equatorial positions. They have more room then. Remember, the whole basis of this theory, right, of our shape is based on the fact that our electron groups want to have as much room as possible. So for my 5 electron group structures, when I have a lone pair, I'm going to put it in one of those equatorial positions. So I can put it here, here, or here. If I was to put it in one of those axial positions, I am going to get the wrong answer. I'm going to choose to put it in the one that's in the plane, but you could choose to put it in any of those positions. So sulfur in the middle, I'm going to go up to a fluorine, down to a fluorine. I'm choosing to put my lone pair right here. Again, I do want to see that orbital. And then I'm going to have 1 fluorine coming out, and then 1 fluorine going back. Bond angles on this one. This one is actually going to be a little less than 120 degrees. Again, that lone pair is pushing those bonds a little closer to each other, so less than 120. And then my 90-degree bond angles are actually still 90 degrees. They're not less. So 90-degree bond angles between my axial position and all of my equatorials. So I drew one, but I could have drawn it here instead, right? Or I could have drawn from the bottom, I could have drawn from the bottom to this one, or from the bottom to that one. It would be underneath, it would be behind that fluorine that's coming out at us. You don't have to label all of them, just make sure again that you don't label here. That would be wrong, right? Because it's not a bond angle, or here. And then only one spot to label my less than 120, right? I only have one bond angle with my equatorial positions. So the name of this one is actually kind of funny. It's a seesaw. And we'll look at the models after I do the next one, but you can, once I make the model, it's easier to see where the name comes from. But essentially, if you were to take this structure and tip it sideways, so I have the sulfur, and then I have the fluorines, and then one fluorine's coming out at us, and one fluorine's going back. So it's like this little teeter-totter. This is the fulcrum. And then like this is where you would sit, and then this part would like go up and down. So seesaw. Next example. So I have chlorine trifluoride. And again, please practice doing these Lewis structures on your own. And then when you're ready, hit play again. So this one, it's the first time we've had one where I have all halogens, right? When we were doing our Lewis structures, we said halogens normally don't go in the middle. I don't have a choice here, right? All I have is halogens. So chlorine is the less electronegative one. It's also the one that I have one of. So I'm going to put chlorine in the middle. I'm going to bond it to my 3 fluorines. I have lone pairs on those. And then after you do that, you'd find that you have 2 lone pairs left over. You have 4 electrons left over. So they go on the central atom. So 5 electron groups, 1, 2, 3, 4, 5. Of those 5 electron groups, 3 of them are bonds. And then 2 of them are lone electron pairs. And again, our lone pairs have to be in the equatorial position. So this time when I draw it, I'm going to put my lone pairs actually coming in and out. So I'm going up to 2. I'm going up to this here. And I'm going to put my lone pairs in those 2 positions. You can put it in any of the 3 equatorial positions, but again, they have to be equatorial. So lone pairs, right, must go in our equatorial positions. So I'm going to have chlorine in the center. I'm going to go up to a fluorine. I'm going to go down to a fluorine, and then out to a fluorine. And then remember when we have our lone pairs coming out, we're going to kind of shade the end of that electron cloud, and then the one going back is going to be dotted. What do we have for bond angles? Yeah, good. Hopefully you said just 90, right? I don't have any 120-degree bond angles anymore because I only have one equatorial bond, right? Remember, bonds between, angles between bonds and lone pairs are not bond angles, so only 90 this time. And I would have 2 of them. I could label there, or I could label here. So 90 degrees. And then the name of this one is T-shaped. If you were to tip it sideways, it looks like a T. So T-shaped is the name of that one. One more example in this group, and that's going to be I3-. So just 3 iodine. So iodine in the middle goes to another one. Lone pairs on my terminal atoms. When you figured out your total number of valence electrons in step 1 for drawing Lewis structures, you would find that you have 6 left over, so I'm going to have 3 lone pairs on that central atom. And then this does have a -1 charge, which hopefully you took into account when you determined your total number of electrons, right? If it was negative, we added an electron. So I'm going to put those brackets around it. So on the central iodide, I have 1, 2, 3, 4, 5 electron groups. Two of them are bonds, and then 3 of them are lone pairs. And again, those lone pairs have to go in the equatorial positions. So I'm going to have an iodine in the middle. I'm going to go up to another one. I'm going to go down to one. So again, they have to be, my bonds are going to be axial. My lone pairs have to be equatorial. So I have a lone pair in this position. I have a lone pair coming out at us, so I'm going to shade this one. It's kind of a bad shading job. It's just getting worse. I'm going to have one going back. So bond angle on this one, normally we don't cut through a lone pair when we're doing bond angles, but I don't have an option. The only way to do a bond angle on this one is to actually cut through our lone pair, right? Because that's the only bond angle I have. What's the angle between those? Yeah, it's 180. Good. So the name of this one, I have 3 atoms and they're in a straight line, right? They're not bent, they are linear. So that's going to be all of my 5 electron group ones. Let's go out to that handout and we'll draw our little structure here. And then I am going to add the axial and equatorial to it, so that way in your notes, because I'm going to write something about where the lone pairs go, you'll have that. So lone pairs go in the equatorial position. So same idea that we've been doing, right? Every time I replace one of those bonds with a lone pair, I literally do that. I replace a bond with a lone pair, but we do need to keep in mind that this time, right, my little asterisks, the lone pairs have to go in the equatorial position. And then my electron domain geometry is basically just that. So Trigonal Bi Pyramidal. So I do just want to show you the shapes for those other 5 electron group bonds. So I do have my Trigonal Bi Pyramidal here, and then remember our lone pairs are going in these equatorial positions. So the first one, where I just have one lone pair, is this. So we were drawing it with our lone pair in the plane, and then one equatorial coming out and one going back. And then I said the name was based on the fact that if you tip it sideways, it looks like a seesaw. So I'm going to do that. I just took it and I tipped it sideways. So those two are my little fulcrum, and then it's like a seesaw or a teeter-totter, whatever your preferred name is. They call it seesaw though. So it's a little seesaw. If I was to have another lone pair, it's also going to go into an equatorial position. So I'm going to take that off. And now I have 3 things, and if I tip it sideways, it looks like the letter T. So T-shaped, right? Just 90-degree bond angles this time. And then our last one is this guy. So I do have lone pairs in all 3 of those equatorial positions, but the name of the shape is just based on the fact that I have 3 atoms in a row, so linear 180-degree bond angles. Just our 6 electron group ones left, and we're actually only going to do 3 of those. As you can imagine, there's more, right? The more bonds we have, the more bonds we can replace with lone pairs, but we're just going to do 3 of them for our 6 electron groups. So going out and doing our examples. My first one is going to be SF6. And when I draw the Lewis structure, which hopefully you're also doing, I end up with 6 fluorine, which I didn't leave enough room for, attached to my sulfur. And when you go and put the lone pairs, each fluorine has 3 lone pairs, giving it an octet. Sulfur has 12 electrons around it, but that's okay, right? It has d orbitals available to it. So if I look, I have 6 electron groups, 1, 2, 3, 4, 5, 6. All of those are bonds, none of them are lone pairs. So 6 electron groups. 6 bonds, no lone pairs. So when I draw this one, sulfur is going to be in the middle. I'm going to go up to a fluorine. I'm going to go down to a fluorine. And then I'm going to have on each side one coming out and one going back. So a fluorine coming out, a fluorine going back, a fluorine coming out, and then a fluorine going back. All of those bond angles are 90 degrees, right? I have 4 around the middle, so between here and here, here and this one, right? This one around the back, and that one, right? Because there's 4 of them and they're all in the same plane, they're going to have 90-degree bond angles. And then between my top fluorine and all those ones on the side, 90 degrees. Between my bottom one and all those ones on the side, 90 degrees. So I don't have axial and equatorial positions on this one because all of my bond angles are the same, right? The reason this one, we were considering those positions different is because my bond angles were different. So for this one, every time I replace a bond with a lone pair, it's not going to matter where it goes because all of those bond angles, again, are the same. The name of this one is octahedral. If you were to connect all of those atoms, you actually have an octahedron, that geometric figure. I would try to draw it for you, but it wouldn't look like it if I tried, so just you have to trust me on it or look up pictures. But octahedral. I have actually heard it called square bipyramidal before. That's not very common, but there's 4 around the middle, so square, and then up to a pyramid and down to a pyramid. But octahedral is what we're going to call it. And then we're just going to keep doing what we've been doing. So I'm going to draw my kind of generic one here. So remember, on each side I have one coming out and one going back. And then every time I replace a bond with a lone pair, I'm literally going to do just that. So our next example, I have antimony bonded to 5 chlorines and it has a negative charge. Hopefully, even though I've stopped telling you, you've still hit pause and go draw this. So I end up with lone pairs on all those chlorines, and then from your initial electron count, I would have 2 electrons left over. So we're going to put that in brackets with the negative charge. I think I did up here. I forgot to do that with iodine. Yeah, it's still standard until we do formal charge, which we will do in this chapter. Until we do that, it's still standard to put those brackets around it with the charge. Sorry, I forgot that one up there. I also haven't been putting lone pairs when I draw my molecular geometry on my terminal atoms. It's pretty common not to. They are still there, like on this one. That fluorine still has those. They haven't disappeared. It's just that what we're really focusing on is the shape on that central atom. If you're drawing Lewis structure, now I have to account for every single electron, so those have to be there. If on the terminal atoms you don't put them on the shape, I'm okay with that. They have to be on the central atom if they have them, but on the terminal atoms, when you're drawing the molecular geometry, if you don't put the lone pairs on them, it's okay. On the Lewis structure, they have to be though. So if you're afraid that you're going to forget when and when you don't need to do it, just always put them there and you'll be safe. Okay, my shape for this one. Oops, sorry, 6 electron groups still. This time, 5 of them are bonds, and then 1 is a lone pair. And again, because my bond angles are all the same, it doesn't really matter, right? When I go to this structure, which position I want to put those lone pairs in. I tend to put it on the top or the bottom, and honestly, I switch between the two. If you want to put it in one of the ones coming out or back, that's fine. Just make sure you shade or dot your orbital appropriately. I'm actually going to put it on let's put it on the bottom. So antimony in the middle. I'm going to go up to a chlorine, and then on each side, I'm going to come out to 1, and then go back to 1. It's getting kind of too messy. So chlorine, chlorine, And then down here, I have a lone pair. So the name of this one, I have 4 around the middle, so square. And then it goes up to make a pyramid, so square pyramidal. Not bi, because I'm not going down to a pyramid, right? I'm only going up to a pyramid. So square pyramidal. Bond angles, I actually have 2 different bond angles here. So remember, this lone pair takes up more space. So what it's doing is it's actually pushing all 4 of these, right, the 4 that are in that planar square, up. So my bond angle between this one that's on top and the ones around the middle are actually going to be less than 90 degrees. However, that lone pair is pushing all 4 of those up the same amount. So the bond angle between here and here is still 90 degrees. And then, again, until we do formal charge, I want to see brackets with that negative charge. One more example, and then we are through our chart. So our last one, I have Xeon bonded to 4 fluorine. And when we draw our Lewis structure, I end up with 3 lone pairs on each fluorine. You'll find that you have 4 electrons left over, so both of those go on the central atom wherever you can fit them. So 6 electron groups, right? 4 bonds and 2 lone pairs. And then it still doesn't matter if the lone pairs are axial or equatorial. This one does have a stipulation though. Remember that those lone pairs take up more space. So what I want to do is I want to put them across from each other. So you want those lone pairs to be 180 degrees from each other. So if I put the first one in the bottom position, I'm going to go back up to my basic structure here. If I put the first one here, then the second one has to go here. So they have to be across. If I put the first one, oops, sorry guys. If I put the first one, let me get that bond back. If I put that first one in this position, then the second one has to go in that position. So they have to be 180 from each other. I don't particularly like wedging and dashing our orbitals, so I'm going to put them top and bottom. But again, it doesn't matter. It only matters that they're 180 from each other. So the lone pairs, the 2 lone pairs, it's not a bond angle, but that's the angle that the lone pairs must be from each other. So I'm going to do Xeon in the middle. I'm going to go up to a lone pair. I'm going to go down to a lone pair. And then I'm going to have a fluorine coming out and going back on each side. 2 coming out. And then 2 going back. What do I have for bond angles? Just going to make that look a little nicer. Hopefully you guys are thinking just 90 and you're going to be right. So 90 degrees between those 2, the 2 on the other side, but then also these 2 are 90 degrees. And we will look at a model of this one here in a moment. The name of the structure, square, because there's 4. And then remember, this shape is based just on the bonds, right, on the atoms themselves, not the lone pair. So I have 4 things in one plane, right? I don't have any atoms coming up. I don't have any atoms going down. So square planar would be the name of this one. So let's look at our models. So our octahedral structure. So my one on the top, the one on the bottom, and then kind of how I've been drawing it, I have 2 coming out at you, and then these 2 are going back behind. So 90 degree bond angles between the top and all these ones on the side. between the bottom and all the ones on the side. And then when I tip it, right, all these ones around the middle also have 90-degree bond angles. The first one that we did where we replaced a bond with a lone pair, I took up the bottom one. So square, right, I have 4 around the middle, and then it goes up, right, to form a little pyramid. So square pyramidal. And then remember, if you have 2 lone pairs, they have to be across from each other, right? They have to be 180. So I'm going to take the top one off, and I have this guy, which is square planar, right? I was drawing it in this orientation where 2 are coming out and 2 are going back. Nothing's coming up, nothing's coming down. If I wanted to draw in this orientation, that's fine. Then nothing's coming out and nothing's going back. But 4 things in just a plane, right? Completely flat. So square planar. I want to go out to that handout one last time here. And we'll add our octahedral structure. So on each side we have one coming out and one going back. So our electron domain geometry, octahedral. And then remember, if I have 2 lone pairs, they have to be across from each other. So if I put my first lone pair here, my second one has to be here. If I put my first one here, then my other one has to be there. So if you have 2 lone pairs, just remember that they must be completely across 180 degrees from each other. So we can write that little stipulation. If 2 lone pairs they must be 180 degrees from each other. So again, the easiest way for me to learn these is to really just remember this column right here, the number of electron groups, and then remember these basic structures. Because if you can remember that one structure, essentially you're taking, like if I look at the Trigonal Bi Pyramidal ones, you're taking all of this and you're really narrowing it down to that one little picture. I think it's a lot easier if you can do that. And then the name kind of looks like what it is, right? You still have to know the names, but I know that if I get rid of this part, right? If I tip it sideways, it's a seesaw. I know that if I was to get rid of those and then tip it sideways, it looks like the letter T. So I would focus on trying to learn these basic shapes. I really think it helps if you try to find things that they have in common, right? If you look at this entire table, it can be overwhelming because there's a lot of information there. But if you can narrow it down to just those first couple columns and then be able to figure the rest out, it helps a lot.